Hey, good morning. Just want to welcome everybody to the April ECSS Symposium. So we've got two great talks lined up today. So the first is going to be by Paul Rodriguez, one of my colleagues here at the San Diego Supercomputer Center, a case study on deep learning for classification with imbalanced finance data. And that's going to be followed by Mitchell Dorrell from the Pittsburgh Supercomputing Center, reworking inefficient workflows for shared HPC resources. Just a reminder that since this is an XSEED event, we are governed by the XSEED Code of Conduct. I'll just leave it up here for you to read. If you have any questions or concerns, you can contact our XSEED ombudspersons, Linda Ackley, Lizanne DeStefano, Ken Hackworth, or Brian Sneed. And there's a link, and I'll take this and paste it into the chat. Just one sec. And we'll just give it another minute or two. But then folks are still trickling in. So Paul, did you decide, would you like to take questions as we go along, or would you prefer that we wait until the end?
Let's wait till Thursday. No, sorry. No, it's fine. I'm fine either way.
Okay, good.
Questions are welcome during that's fine.
Okay, great. And Mitchell, any opinion? Would you like to take questions during or save them till the end of your presentation?
For me, definitely during.
Yeah, definitely during. Okay. And I mentioned yesterday to both of you, don't worry about monitoring the chat. I'll be keeping an eye on the chat window for you, and then I'll chime in when there's a when there's a good pause, say at the transition between slides.
Okay.
You see, okay, we've got 31. Let's give it one more minute, and Paul will get you started, I think, at 10:04. All right, what looks like attendance has leveled out. So Paul, whenever you're ready, go ahead. You can share your screen and take things away.
Okay. So I'm Paul Rodriguez. I work at SDSC. I'm assuming people here know me. So this is a project with Jim Albertus, who's at Department of Finance School of Business in CMU, and Brian Gill was also part of the project, and he really helped get a lot of things going in the beginning. And so I'm calling this a case study on deep learning. Really, let me go ahead and move my slide. So the goal of the PI's work is to explore association between some of these financial data issues and some modeling. And so there's a growing interest in finance literature, of course, just like everywhere else with deep learning. But my role here is, of course, as ECSS and IP person, is really to focus on the modeling, the methods, and getting things to run efficiently. So for this presentation, I'm gonna, I'm talking about the modeling and the results of the modeling. So as I said, people are interested in deep learning, but it hasn't had a big impact on structured data, so tabular data, or 2D, sometimes I call it 2D data. They haven't had such a big impact on that kind of data. So we're going to run this and compare it to other machine learning models, and also, deep networks versus shallow networks. The problem here is a prediction task with a low positive case rate. So we have a really high imbalanced data, and I'll talk about that some more. So we're going to look at sample weighting and different ideas of how to incorporate different weights for machine learning, or neural networks in particular. We're also interested in variable effects, like trying to understand what when the model is doing well, what are the variables that are important, let's say. This also started, we also started this project with the idea that we would look at recurrent networks because there's some time component here. And so I'm going to talk about a little bit more about that, although I don't really have a full analysis. But we'll get on to that. So so the challenges for this data set. So again, as I said, it's really highly imbalanced. The positive cases only occur like 0.7%. And the thing about neural networks is they often require more data than other models. So it'll be interesting to see how it performs. One reason we want to look at this is to see how it performs with imbalanced data. So it's a good case study to look at, performance, regularization, all these issues that come up in machine learning and see how deeper networks might do. And of course, there's this other question that the PIs would address is, these questions about financial variables and maybe nonlinear effects in models more generally. All right, so let's talk about the data. The data set or the data. Yes.
Before we go on, we have one question from Kenneth Yashimoto. He's asking, What is a positive case?
Oh, okay, I'll get into that.
Okay.
So we transform the data. So we have this big data set that Jim curated and got from some databases, from industry databases. He combined different data sources. So he did a lot of this upfront work. There's a bunch of measurements that are related to financial, information from firms. There's some indicator variables. There's a type of firm variable that has a lot of mutually exclusive binary indicators. So that's not unusual to see that kind of thing in a regression framework. And all the variables are standardized. And what we're trying to do here is predict bankruptcy. So the positive case rate that the question was about is refers to the fact that in this data set, we have a certain number of bankruptcies. So in summary, there's 38 years worth of data, and 7,900 firms. Now, not all firms have data all years. There's 82,000 rows, 180 columns, 612 total bankruptcies across this data set. So it's pretty rare. If you think about most machine learning cases that you look at, there's much more of a balance if you're trying to do classification. But it's not uncommon to see this kind of imbalance in a lot of data sets. Okay. So the task is to predict bankruptcy for the next year. And so with this data set, one of the challenges is to figure out how we're going to do cross-validation or something like cross-validation. You want to do a validation so that you can estimate your parameters and also get an estimate of how well you're going to generalize. So because the data is also temporal, you don't want to look ahead. You want to make sure that all your predictions are only based on data you have up to a certain year. So we consider a split year, and as what we're calling the year where we cut off training data. And then the validation year is the next year. You're going to look at data for the next year and say, oh, is this firm going to be bankrupt? Okay. And again, so the challenge here is that, when you do cross-validation, you typically want to have a validation set and then also have a test set that is sort of unseen. You don't want to use the test set in any way while you're picking your parameters, your hyperparameters especially. So we split the data up this way. We have 10 years from 1977 to 2006 where we're doing training and validation. So we're going to train up to 97, predict 98, train up to 2006, predict 2007. And then we're going to use the other split years are going to be 2007 to 2016, and we're going to use those to estimate the generalization error. Now, cross-validation typically works different ways. We're kind of constrained because we don't have a lot of bankruptcy cases. In other situations, if you had more data, you could maybe do cross-validation maybe across firms and still keep it causal. But so we have, this is not necessarily the ideal situation. And you'll see why as we go along. Okay. And the other thing is because we have low positive case rate, we don't want to take the average of our performance for every validation year. So I think it's better to pool all your predictions across each 10-year set. So that means you're going to get a better estimate of your expected error, but you don't have, let's say, a sense of the variance, how that might vary from year to year. And we also, as I said, arrange this as sequential data, where we have, in this case, it's a 3D data set. It's going to be the number of firms times the number of years times number of columns. Most firms, don't, as I said, don't have the whole 38 years worth of data. In fact, the average, I think, is something like 10 years worth of data in this data set. There's different times when the firms appear and don't have data. So it could be, they're there from the beginning. It could be they're there and they don't start till 1990s or something. Some of the firms, or in this case, as I say here, 833 of the original 8,000 firms, they had missing segments. So that means they had data for a few years and nothing for a few years and data for a few years. And sometimes that's related to bankruptcy. Sometimes it's related to the fact that they were, their total capitalization was small and they didn't make it into the database. So there was a cutoff from this database it's an industry database. So we cleaned those up. We didn't remove all of them because, as I said, some of them were bankruptcies. We don't want to get rid of too many bankruptcies. So that means we're going to have some data in the sequence where you have a firm that has data for several years, nothing, and then some more data. And we threw out the ones that had too much missing. So if they had more missing years than they had years present, we threw those out. Okay, and just a quick description of the data. So on the left is the number of bankruptcies across years. On the right is correlation of variables to bankruptcy target. So as you can see, when you look at the number of bankruptcies, it's not, it's not like like Brownian motion. It's not completely noisy. There is like sort of temporal component. There is a little bit of dependency from year to year if you were just looking at this as a time series. The spikes you see are, they're related to some real world events. The actual percentages are a little bit different than this. This doesn't take into account, this plot doesn't take into account the fact that there were, more firms, or some years had more firms. There were firms joining this list. So the probabilities are a little bit more squeezed together. The probability of a bankruptcy, but the general shape shows, how bankruptcies change across years. There was no particular variable that had really high correlations on the right side. There was a few variables, there's one that kind of stands out around 62, and this one will come up again. Okay, so the model scripts, all neural networks. Again, I'm using TensorFlow Keras 2.0. This is all run on bridges. All this is all run with regular CPU nodes. All these models were implemented using sklearn or scikit-learn. And the runtimes for these things, they vary a lot depending on how big of a hyperparameter search you do. So the regression models, they don't have as many hyperparameters. Again, I'm running this for 20 years of data. The nonlinear models, especially the ensemble models, can take a long time depending on how you set up the hyperparameters. And we'll talk a little bit more about that. I organized this a little bit differently than you would typically organize a workflow for neural networks. Typically, you come up with a configuration. You say, I want to test these parameters, these hyperparameters in this architecture, and I'm going to run it with my cross-validation data set. But here, since I'm trying to pool predictions, I need to save predictions. I didn't want to create too many files. So I kind of organized everything around doing 1 year at a time. And then for that 1 year, I would run the models, produce all these predictions, and I would save it in a CSV file where I could then sort it later. Okay. So I found that to be, as I said, I don't know if that was always the best way, but it worked. Okay. So the big thing about neural networks, of course, is that there's so many, compared to other models, there's so many hyperparameters. You're choosing architectures, and this is not even, not even the regular parameters. This is just to start with. So what I did was I started, I plan to do a systematic search with layers, units, and the learning rate, because these are the kind of main parameters that could affect how well a network is going to, produce nonlinear representations of whatever the problem is. So once I did it, I started out doing a search with just trying out different values, and then once I got an idea of where values, are performing decently, then I started searching through different architecture options, or different other options, like the activation units, whether or not we should do, some kind of normalization, in the literature and the Keras API documentation. They often describe certain kinds of options that you could take. So, looking at the literature and some of the Keras recommendations, I opted to use like a bias initialization for the output activation units. I found that the SELU, which is the scaled exponential, works probably a little bit better than rectified linear unit, and that's what was in the literature, that was proposed in the literature. I used the atom optimizer, so I didn't really spend time looking at different optimizers, just because in the literature, people say atom is kind of, it does seem kind of more flexible, and it is kind of a later version of all the optimizers that are out there. There's this idea that skip connections can be very important, where you take your outputs from one layer, you skip, and you don't pass it to the next layer. You pass it to the next layer, but then you also pass it to a layer two layers ahead or something. And there's some different variations like that. I did do a little bit of the skip connection testing. And the reason it's relevant here is because people suppose that that's really going to help deeper networks. Okay. All right. And as I said, once I got an idea of some of the bigger architecture choices or activation choices, then I did a grid search. I compared grid search and a hypertune. So there are in Keras and there's other tools out there to help you do a search. And the whole idea of a search, of course, is, if you haven't heard this, for something like a discrete model, like you're choosing discretely whether you have 4 layers or 5 layers, for example. You kind of want to do this exploration and exploitation trade-off. So when you want to explore different parts of your space, but you also want to exploit, when you think you have an idea of where the best values are, you just kind of search around there. So the hypertuner class implements several search strategies. The hyperband is the one I use. It's kind of runs like a little competition with incremental training. A lot of people like this Bayesian optimization, or that seems to be getting a lot of mentions in articles. And it's really doing something a little bit different. It's using like a function approximation to sort of figure out where to search the space. So I haven't tried that one yet, but I'm going to probably test that at some point. So I ran a little test where I looked at the hyperband search versus a grid search using the same set of choices. And both, they run in about the same time. So, this network, so this is, again, 80,000 rows training, running through 225 combinations. And this was for just one year of data, 1 year of validation data. So they ran, as I said, about 40 minutes. Both of them find that, small networks typically do better than deep networks. Sometimes the deep networks can perform near some of the top scoring networks. But in general, both searches came up with this kind of range of small number of layers. So this is, as I say, there are 2 layers, 64 to 256 hidden units. The learning rate range seemed to be, like around 0.005, more or less. So then once I got that, then I use a more fine grid search to search over this, this more focused region. And then I picked out the best hyperparameters. So again, I'm running this on the validation years. Okay, so the metrics, if you've done machine learning, this kind of, these kinds of studies, you would be familiar with the area under the curve. I think these are sort of more robust than accuracy measures, for example, because you're testing the model under different, a different set of thresholds. The precision recall curve is something that comes up more for this kind of data, imbalanced data set or information retrieval kind of stuff. Okay, and in both cases, you're looking for higher numbers. So here's what the results look like. On the left, okay, so on the left column, I got the different models. The regression models are the first three, and then the next two are the ensemble models. I ran a neural network with some good set of hyperparameters, and then I ran an ensemble of neural networks. So in bold, I have a couple things to highlight. I don't want to go through all the numbers, but the gradient boosting model actually has the highest ROC AUC value. The random forest has a higher AUC for the precision recall curve. And if you look at what the random forest is doing, it's only predicting a small number of true positives. But when it does that, it has a small number of false positives. So by being a little conservative, it can come up with a better trade-off precision recall. Now, all these precision recall scores, though, are pretty low. They really should be closer to 1 for a really good model. That's what you would get with a balanced data set. With an imbalanced data set, it's, you're just going to get lower scores. Again, the base, so as I maybe didn't see it before, but the baseline for this kind of for area under the curve for a precision recall is usually can be as low as the base rate. So, close to 0. So it's not that these are doing bad. It's not that they're not learning anything. It's just that it's a hard problem. So we're not getting values, close to 1. Okay, but now what's interesting about the neural network is it actually is very much less conservative in terms of trying to predict the true positive cases. So it had, in this case, 52 out of the 151 positive cases, it did predict. And when you use the ensemble, you do get a reduction in the false positives. So the ensemble doesn't necessarily help you find a better part of the space to make more true positive predictions, but it definitely eliminates some of the false positives. Okay. And then I looked at, well, let's look at the predictions through the years. So here I'm just looking at the neural network ensemble. The blue line is the true number of bankruptcies from year to year. The red line is the number of bankruptcies predicted. So not all of these were true positives. It's true positives and the false positives. And you can see that there is information, even though I'm not explicitly giving it sequence information, there is information where every year it kind of can make predict more bankruptcies. Especially in the last 10 years, we see this the shape of this curve follows pretty much the blue line. The shape of the curves are pretty similar, and you can see where we have years that are due to external events where there's some kind of big spike in bankruptcies, or relatively big spike in bankruptcies. The networks are, that's where the errors are. That's where the bigger errors are. Okay, and the other question is, the other thing we see here, if you look at the validation years, there is this long decline in bankruptcies for a good 6-7 years or something, and so that's kind of a trend that's happening in those years. That's not happening in the next set of years. So there is there's a little bit of difference in your statistics of your validation and your test sets. Okay, and so we're considering adding another variable for previous number of bankruptcies to see if some of this can be improved. Okay. Okay, so just a couple notes about programming. There's, as I said, there's a lot of other models, and I didn't talk about the other models and the kind of hyperparameter search that's involved. And I didn't run a support vector machine. If you're familiar with machine learning, that's kind of a model that sometimes people say do well with small cases. I did try to do the kernel ridge regression, which should be similar, but those jobs weren't running well, so I have to revisit that. Then we did a sample weighting scheme. So this is where you have an option to fit your model and you weight the classes. And I'm just going to skip really quickly how this went. There's a particular version of random forest that actually performed really well. And so all the models make a lot more true positive predictions. So here again, the neural network is, is pretty competitive. It's okay. But again, the balance, so this balance random forest, it's a different kind of ensemble method because it undersamples the negative cases. Okay. So then our other thing we tried, we wanted to look at custom loss functions, and Jim had the idea of using market capitalization. So we explored this possibility. We programmed our own loss function. We didn't get great performance in the sense that we still had a lot of false negatives. And so we have to revisit this and look at how to properly scale market capitalization. So it was doing a little bit worse. Oops, I'm sorry. It was doing a little bit worse than just weighting by class weight. So that's the kind of thing we want to keep, we're thinking about. And the idea is that if you could find, some scheme where you don't lose as much money, maybe you don't make as many great predictions, but maybe you can avoid losses from false negatives, then that would be interesting. Okay, so just a couple programming notes for those of you who are doing Keras or trying to build neural networks to use custom functions. Keras is pretty good about having places where you can build custom functions, but it doesn't always pass the data that you need. And in this case, it doesn't pass row information when it wants you to, if you're trying to build your own loss function. And so we needed that to figure out which rows, what the market cap values were. And there was two ways to do it. And I just have those listed here. So you have to be careful when you're doing, this kind of stuff. In one case, I think it would work really well. You could work it with different batch sizes, but then you have to also customize your metrics. In another case, you could just use the batch size of the whole input, and then you could figure out what your input is.
Paul, let me interrupt you. We have a question in the chat. This one from Madhugujral. Do scikit and AI libraries impute missing cells data using some regression model?
I'm sorry, say it again. Is it in the chat?
Yeah, so it's basically about imputing missing values. So question was, do scikit and AI libraries impute missing cell data using some regression model?
Well, remember, I'm not imputing data here because if a firm, because when I'm using the 2D data, I'm not presenting it as a sequence. So I'm only presenting, 1 year, one observation is for each 1 year for each firm. So when we do the recurrent network, then, and we want to if we want to do like, so the question would be relevant if we were running our models differently. But so I didn't really have that issue. And I don't really know how the scikit-learning does imputation, to tell you the truth. But I didn't really have to try to do that. I don't know if that answers your question. Yeah. That's a good question. But if we had that situation, again, some of these firms were missing like 3 or 4 years of data in a row. So I would be really suspect of trying to fill in missing data like that. Especially if a firm has, let's say, only 15 total years of data, maybe they're missing a segment of 5 years of data. Really, that would be hard to fill in. Anyway. Okay, so we started looking at recurrent networks. I didn't get as far as I'd like to, but I'm running out of time, so I'm gonna do this one quickly. But the nice thing about recurrent networks, so the implementation that Keras has, it will have this option where you can give it a mask. And you tell it, okay, I don't have any data here in the beginning because the firm didn't exist. I don't have any data at the end because the firm, didn't have more data after 2008 or whatever. And if you have, and so you can give it a mask, and the network will just say, well, I'll just assume there's no return state and just output, whatever the last output was. So that's what's happening in this example. The blue line is data, just one, not one variable. It's like the maximum value of variables, of some of the variables. So the blue line is like, okay, there's a bunch of data coming in. The orange line is the target. Here's a firm that had two bankruptcy occurrences within an 8-year period, I guess. And the green dots are the model predictions. So in the beginning, there's no data. So it's just predicting 0.5, which is the midpoint of a sigmoid activation. And then it starts getting some data. It makes low predictions, and it doesn't predict the first bankruptcy, but it does a pretty good job predicting the second bankruptcy. And after that, it just keeps outputting that prediction because there's no more real data anyway. So the recurrent network implementation of Keras handles this way by default. And so as long as you give it the right mask, you can deal with it. And then you just have to make sure if you're post-processing your predictions, you take that into account. So the masking, there is a couple variations on how you do masking, and just using a masking layer worked for us. Again, we had to just go through and run a lot of verification to see that it was doing what we think it should do. Okay, and that's just summarizing what we were thinking about. So finally, I just want to say, I don't have the summary. Hang on. So we didn't really get great results so far with recurrent networks. I haven't really done a grid search or hyperparameter search. I've really just started with the hyperparameters from the feed-forward network cases and just said, okay, let's just try a few of those. So I need to go back to that and give it a proper test. The other thing I was we were looking at is, some of this explainable AI stuff. So the integrated gradients is something that is an idea that's been coming out in the deep convolution network literature, and it's a way to measure dependency at pixels or really at any input value. And the idea is you take the derivatives and you integrate a derivative value over some range of your input. So I got a little picture of this. Keras uses gradient tape functions. If you haven't had to look at how Keras is doing gradients, it's actually, they make it relatively straightforward. Just a little bit, the coding isn't too hard. It's not always clear exactly what you have to give it in order to track your gradients. Again, this integrated gradient idea works really well in images because then you can see like what part of the image an output is responding to. The problem is you have to be careful how you choose your baselines. And in our case, because we're not dealing with an image, we're dealing with a variable that's real value. We should be looking at some range of values where those variables are actually used or actually have value. So what I'm plotting here for one of these variables, so this is the variable that had the highest correlation with the target. And I'm plotting the output activation as this variable goes from negative 15 to 25. But this variable after standardization, usually it's mostly occurs with values between negative 1 to 6.
Paul, let me interrupt you for a second. Where you're either going to have a lot of time to answer questions or very little time for the questions. Our second speaker, Mitchell is ran into a problem that we've never had before on a symposium, and it appears that he has lost his power in Pittsburgh. So he's in on the phone. Mitchell, if you just want to unmute, let me know. Have you come up with a solution, or are you going to, or should we just reschedule you for another ECSS symposium later in the year?
Can you hear me?
We can hear you.
Okay. So I'm trying. I thought I could pull some older data from Overleaf, but I'm having trouble getting into Overleaf on my phone as well. I don't want to keep people waiting, but I mean, you know, every 30 seconds there's a chance that I'll figure something out, but there's also no guarantee. So
okay, so how about we do this? We'll let Paul finish up. I know that you're still actively working, and regardless what happens, I think we're just going to go ahead and reschedule you, and that way you can, you know, do the presentation the way it was, you know, the way it was intended to be done. And
yeah, this is
and,
news for me as well. This is my first actual outage here in Pittsburgh, and
yeah.
so yeah.
And then maybe when Paul is done, you could just say a few words about your project as a teaser, and then we said we'll reschedule.
Okay,
So,
all right, sounds good.
All right, so Paul, we'll hand things back to you. Don't take too long, but go ahead and finish up.
Okay. Okay, I had a question. Let me just finish this point on this slide is that one way to measure dependency of your input is to use this idea of capturing the gradients, summing them up over some set of values, and give a score for your input as a reflection of the dependency of the output for the input. But the trick is that you have to figure out how to vary your input. How are you going to vary all the inputs together? So there's a couple different ways to do that. And I just did a basic copy of how they do it for images. And I came up with a measure of dependency. And then I plotted the correlations between, okay, so this on the x-axis, I plotted a correlation between my integrated gradient and the actual correlations to the target. And so you do find, like, there is a linear trend here. So variables that are highly correlated to the target are going to show up as having strong dependency on the target. So that's a little bit, that's kind of satisfying. That's the kind of thing you would expect. There are some variables that don't necessarily have strong correlation to target, but do have strong dependency strong dependency values. So those would be variables you could explore and look at further and try to see why that might be the case. Okay, let me see. So there was a question, and oops.
Hi, Paul. I can read out the question if that's quicker.
I'm almost there. Okay.
Okay.
Are you building these models from scratch, or did you use tools? Okay, so the models are all built using scikit-learn. So sklearn has all these models built in, and that was part of. So are they on bridges? They're really, you got to make sure you have the right singularity on image. So these are all using the Python, Python scripts, and so I was using the latest singularity image that has TensorFlow and scikit-learn. And I think some of the images when I first started didn't have pandas and scikit-learn. So everything, the last singularity image that's there has everything that I've been using. Yeah. Okay. And then yeah. Okay. So I hope that answered the question.
Yes. Thank you. Thanks very much.
Okay. Let me go back to this. So finally, another thing I did is, so there's this, if we're going to run a bunch of models, it's nice to kind of leverage, see how different models might, compare in how they're solving the problem. So I took the network, I took the example of the neural network ensemble. I took the prediction scores. So remember, this is a neural network. I save all the prediction scores from 10 different seeds, and I take the average of each prediction for each time you're making a prediction. And that average is what produced a slightly better set of predictions, right? So it's a little bit regularized. It didn't have as many false positives. So I take those raw prediction scores and then I train a decision tree or a regression tree actually. So it's not really a classification problem. It's just I take the raw scores, whether some value between 0 and 1. So I trained a decision tree on that output. So I'm basically mimicking, copying exactly what the neural networks do, but in one decision tree. And the decision trees are not necessarily models that are really flexible and powerful. They to work well, they require some tuning and some pruning. But in this case, if you're just trying to copy what another model does, you don't have to learn what the right regularization stuff. You don't have to learn the nuances of your input. So this regression tree can reproduce the network classifications. And the nice thing about a regression tree is you can get these other kinds of scores of dependency. So I did that, and you find that the integral gradients versus the variable importance from the regression tree. There's one variable, the variable that has a super high correlation or the relatively high correlation with the target. That's the only variable that shows up as being important for in both methods. So we get a lot of variation in these other variables. So this would be the kind of thing if you wanted to explore, gee, what is the network doing? How is it different than other models? You could look and here's two models here's two sets of measures that are based on actually the same, two models that produce the same output. And so you can compare these kinds of things. And that's the kind of thing that I think could be useful for the question about how do we look at this financial data. Okay, so this is now summarizing. Just some practical experiences. Again, the very deep neural networks, they don't seem to really be necessary. It's not that they're, that necessarily or uncompetitive. 2 hidden layers seem to be consistently, more effective. Again, ensembles of other nonlinear models compare well with neural networks. They're all kind of, gradient boosting has a reputation of being a pretty robust machine learning method. The integrated gradients, which again, that comes up a lot more in convolution networks on images, and where you try to look and see what part of an image is helping you make predictions. But people are starting to get interested in that kind of thing for structured data or tabular data. So some of the finance papers that are in the references that they're also interested in looking at, when a deep network or in this case a network with 2 layers is learning something, can we look at what are the effects of individual inputs? Okay, and I have some ongoing work where I think would be worth doing just to see how they do. Another thing is that we're looking at maybe using a slightly different data set that has instead of bankruptcy, financial distress. So a lot of firms have some measure of financial distress, and not all of them go bankrupt. And so this might be a better way to alleviate the problem of alleviate the imbalance problem. Okay, and the last thing, I do have one slide. I did run so if you're interested in doing neural networks with deep feed-forward networks, and now I was running all this on a regular node, and I was curious at what point I would really want to use a GPU node. So I just ran a test with a large number of layers, 4, 8, or 12, 512 units or 1,000 units, and really as you go up in this example, in this data set size, after 8 layers is when you sort of see a more nonlinear increase in usage time. So after 8 layers and above 512, you start to see this increase in time where if I had to do that over and over again, it seemed like maybe that's when I would really want to go to a GPU. So it's not surprising that the GPU is faster, but it's, the question is at what point do you want to start running all on GPU. So I haven't really run much on the GPU. I think I'm gonna redo this test for this recurrent networks, and that'll be another good comparison. Okay, so there's my references, and if anyone has any other questions, I'm happy to chat.
All right. Thank you, Paul. Now, before we take any questions, as I mentioned earlier, they were having a power outage in Pittsburgh that affected our second speaker. So, Mitchell, I think what we'll do is we could follow up later. We do have one open slot for next month if you want to come back in May.
Yeah, that works for me. If there's an open slot, absolutely.
Okay, great. And I believe there's also in June, but we'll get you in. We'll get you in May if you're available that date. Did you want to say a few words about your project, maybe as a little teaser for next time?
Sure, I will. I'll try not to go over exactly what I put in the abstract, but the gist of it is that we had some interest at PSC for some users to use a relatively new code base called AlphaFold 2. Now, many of you are probably familiar with the fact that protein folding has been a notoriously difficult problem for us to for the scientific community to try to solve computationally. And up until very recently, even the best strategies, even the best techniques that we could use didn't come anywhere close to a human's actually manipulating the proteins and trying to use human logic and human intuition to see how this protein should fold, to the point where there was actually one of the more successful ways of doing it was a group turned it into a game, and it was a game that you could play online where you could get assigned a protein to fold it, and you get a score based on how good of a job you did folding the protein. So that gives you an idea of just how difficult this problem has always been. Up until very recently, when DeepMind, a subsidiary of Google/Alphabet, released their code base called AlphaFold, and the recent successor to AlphaFold 2, which uses some AI-enhanced techniques to basically fold the proteins. It uses some existing databases of sequences and corresponding structures that we know correspond to those sequences, and then feeds them into an AI-based algorithm with the sequence that you're looking to fold, and we'll spit out a couple of different candidates for the ways they think that this sequence might fold, with some rankings for how confident it is that these folds are accurate. And when AlphaFold 2 was released, it set records, and even some experts in the industry have gone on to say that the protein folding problem has been solved now. It's AlphaFold 2 can fold these proteins indistinguishably as good as a human can, and has produced at this point, I believe they just said that they have just folded all of the human proteins, all proteins in the human body that we have sequenced. They have made structures available for. So it's an incredible code base, very, very interesting, very popular, very, there's a lot of attention on it right now, and it's understandable why people might want to use this at PSC. But one of the things that we found out when we went to deploy it is the workflow as released by DeepMind is extraordinarily inefficient. And I personally suspect that DeepMind does not actually use the workflow that they put on GitHub, but the one that they put on GitHub spends the vast majority of its time in basically preparation stages. And these preparation stages are not well parallelizable. You can't really accelerate them using hardware-based accelerators like GPUs and things like that. So while the AI-based portion at the very end runs very quick using the GPUs, all of the work leading up to that, all of the preparation is completely unaccelerated. And it ends up being that like 80 to 90% of your computation time gets spent waiting on between 1 to 3 cores, just doing some number crunching before the actual folding actually begins. So over the past couple months, I've been working on a project to develop a new workflow for AlphaFold 2 that will allow you to run those steps in parallel and basically extract them from the AlphaFold 2 workflow in such a way that users can still utilize the AlphaFold 2 codebase and the AlphaFold 2 algorithms, but in a much more efficient way on PSC resources. So that's, I think that's probably the most, let's say, complete description I can give without starting some extra tangents and leaving them unfinished. So.
Hey, Mitchell, I did an AlphaFold 2 Multimer install on Expanse at SDC. Can I email you? I'd like to ask you some questions about your stuff without having to wait another month to hear them.
Absolutely, absolutely, and yeah, no, I'm definitely willing to help. And you know, it's you know, I have some interesting charts that I could show, showing what kind of speed ups you can achieve when you run these things separately. But unfortunately, they're well, I have them, but I can't show them at the moment. So yes, I'm more than happy to help. I can discuss with anybody over email or you know, however you guys want to reach out. My email address, I can type that into the chat. See here. Okay, yeah, please feel free to reach out. I do apologize for the issues today. I mean, I don't think that this was anything I could control, but perhaps I could have set up on a laptop and a hotspot had I given some forethought to it. This was kind of unanticipated.
This is Yufeng from Iowa State. Can I ask a quick question about the preparation section? I know there's 2 sections. The first part is the sequence, reading the sequence, do multiple sequence alignment. That part, they default to use 8 CPUs, kind of around 2 to 3 hours. It's kind of, then the second part is the GPU for machine learning and energy minimization, Amber part. Now, currently, for the 2.2.01, they are using the Amber GPU to do the energy minimization. That's what exactly you say. The GPU section part currently run very fast. The CPU part is bottleneck right now for small sequence. What do? You recompile that multiple sequence alignment part, use the MPI, and then you allow user to pass in the numbers of CPUs to do the multiple sequence alignment. My question is, what improvement you did for the first part? Currently, they use default alignment using the 4 CPUs and 8 CPUs to do the preparation.
So one thing that you mentioned here is the more recent versions of AlphaFold 2, and I will admit that the code base that I've been working on is version 2.1.1, and I haven't ported forward any of my changes to the more recent releases yet. That is something that I do intend to do before making the code public. But to answer your question directly, AlphaFold 2 calls out to several different external utilities for the MSA preparation for the multiple sequence alignments. Specifically, when you're doing when you're giving it just a typical like a monomer type of folding problem, then it'll call out to Jackhammer and I think it's HH search are the 2 tools that it reaches out to for that. And it actually ends up calling Jackhammer twice, and then HH search, and then Jackhammer a 3rd time before it can start the GPU portion, the model fitting, the Amber relaxation, etc. So what I have done is I have separated that out into several different steps. So that way, if you have lots of different jobs, you can assign them as separate jobs to separate nodes and have a bunch of proteins going through their multiple sequence alignments phases at the same time on several different nodes, or even on the same node. Or what you can do is you can perhaps run that on CPU nodes so that you're not using a GPU node and just letting that GPU node sit idle for hours before it gets to the actual GPU enabled part of the code. So what I've done is less direct acceleration and more I've kind of chopped up the workflow in such a way that users can run the different parts of their workflow on the resources where it's going to run most efficiently. There is intention in the future to open it up a little bit farther so that alternative tools can be substituted. Ultimately, as long as it takes the same input and produces the same output, you can use whatever tool you want to perform the multiple sequence alignment. So that's one of the other goals that I want to approach a little bit later on, is finding some MSA tools that might scale better up to perhaps 128 cores. So that is something that I am interested in pursuing.
Oh, go ahead.
For the current release 2.2.0, it's really good release on the GPU part. They fixed the bug for the multimer prediction. Before that 2.1.0, before that, they have the issues is for the multimer, especially when the protein did not fold properly. More than 2 residues may take the same coordinate at the space. Then the multimer prediction crash. But in the current release, in March, they fixed that issues. And they fixed this relaxation step, make that type super fast because they are using GPU. Before the current release, for relaxation, they were using CPU. It's really slow. And now the issues is the part you are talking about it. Then they did not parallelize this multiple sequence alignment. They didn't allow people using other tools to do this part. The 2.0, my point is that the current release is really needed to for the multimer alignment for the bug they fixed, and also for the memory usage on the GPU card.
So that's very interesting. So I've been doing most of my testing using monomer sequences, and that's just because I'm just running a basic input test to make sure I get consistent and stable outputs. One of the things I was definitely going to do next is run some multimer sequences in order to verify that it works for those two, because they definitely follow different code paths throughout the AlphaFold 2 code base. There's there are references. Obviously, the multimer code does invoke a lot of the monomer code, but like I said, there are definitely some different code paths, and so proper responsible thing to do is to test as many of them as possible. And I hadn't done those tests yet, so there's a very, very good chance that I would have seen those crashes, and I may have been forced to upgrade to the later versions. Although no, I didn't realize that was one of the things that they had fixed. Thank you for letting me know about that.
And Kate, we are, thank you, Mitchell. We're just about at the top of the hour. We can squeeze in one last question. This is from Roshi Sun. Is the new AlphaFold workflow in a forked repo? Will it be merged upstream?
So I don't know, and that is something I am a big proponent of contributing back upstream when the upstream developers welcome these types of changes. I haven't had many interactions with DeepMind yet, so I don't know how welcoming they are to foreign code contributions. But if they are, if they will welcome my changes, then I will absolutely submit them back to AlphaFold 2. If they don't, then they will live in a forked repository in some way, shape, or form. There is also a possibility, and even there is a little bit of a philosophical discussion about what defines AlphaFold 2, right? If you are reusing the algorithms, but you're not using the front end, the workflow that they have laid out for you, are you still using AlphaFold 2? And that's something that I haven't dwelled on too much yet, but it's possible we may have to, in the process of forking it, we may need to change the name as well. So this might end up being PSC fold or something, but we'll see.
Great, thank you. And with that, we are just past the top of the hour. Thank you everybody for joining us. Thanks again to our speakers, Paul Rodriguez and to Mitchell Dorrell. And Mitchell, like I said, we'll follow up and see if we can get you scheduled for May if that works with your schedule. So again, thank you everybody, and hope to see you next month.
Thanks.
Thank you all.